In this video, we will take a look at some of the additional topics in the field. One of the most interesting topics is federated learning. As the name suggests, it's learning that happens in a decentralized fashion across a bunch of different machines which are not under the direct supervision of one entity. So think of it as the data sources themselves are spread across multiple jurisdictions, multiple different organizations, multiple different power centers, and you still need to be able to deal with taking all the data, learning patterns, building models, etc. So this topic is very interesting for the modern world where there are so many devices which rule the roost with respect to how individuals interact with each other, individuals interact with companies, with services, with organizations, with finance, with commerce, etc. And if you really think about it, each of us carrying a device is the ultimate test of federated learning. And we'll see with a very good case study in the next slide. So why does operations matter when it comes to federated learning? If we think of operations as being something that's required and challenging for classical ML or for ML that operates from a data center, the um, the fact that now that ML needs to be in a federated setting makes it even more challenging. I'll call out three specific operational matters which are unique to this topic over and above the set of operational topics that we've discussed so far in this course. First, in a decentralized setting, you are dependent on every contributor of the data source to make the whole bigger than the sum of the parts. So the in federated learning parlance, it's called as clients. Each device is a client, and the client is all distributed, right? You have clients spread across the entire gamut of potential endpoints and connections. So how do you orchestrate these clients? How do you figure out who's available, who's not? Because at any point in time, for instance, our device might turn off, our laptops might turn off. Laptops are also very good, learning agents. So who's not caught up in time? So I could turn off my laptop for, let's say, a week and then come back and switch it on. Whereas all the other devices which are part and parcel of the learning have continuously chugged along in that 1 week. So as my laptop becomes stale, most likely, right, can it not join back into the cohort of devices which are contributing data? It should be able to, right? So that's the common mode of working. So you want to optimize for that common mode. So it should be able to contribute back. So how do you define staleness? How do you catch up with the recent data or the recent weights of the model, etc.? So that's one set of complexity. The second is, how do you take the weights and adjust them to the overall objective? Usually objectives of classical ML learning is minimization of error or minimization of loss, like gradient descent as an example. But those are techniques or algorithms that work great when you've got access to all the weights in one go in a way that's as though it's uniform access. Whereas with federated learning, you've got different contributors to data, each of which never sees the data that belongs to somebody else, right? By definition. Otherwise, it will be like a huge privacy violation. Then how do you aggregate the weights? How do you build a consolidated, holistic model? And there are techniques for that, right? Secure aggregation is one such example. We'll take a look at it in the next slide. The third unique consideration when it comes to the data itself is that um, assumptions about data being independent, right, are usually not applicable when it comes to federated learning. So how do you deal with this non-IID data or not non-identical data? That's the simplest way to think about it. Not independent data, and still have the data contribute something meaningful. That's a problem statement in itself. So if you really think about the key takeaway, how do you preserve privacy of the contributors of the data and deal with the system complexity and reliability challenges of distributing weights, distributing the model, collecting back the weights, ensuring that the model is accurate and well performing while obeying these constraints, right? That's uh, the sum and substance of this particular topic of federated learning. Let's motivate this with a need. And the case study here is Google's own keyboard app called Gboard. It's prevalent in almost all the Android devices and more, right? So if you use a Chrome device, you'll find Gboard there as well. So it's the default keyboard um, that's actually available. Um, the crux of why the keyboard was developed is uh, Google wanted it to get better by learning about typing habits, mistakes that we make when we spell out words, not just in English but also in vernacular. And it's also one of the first large scale successful implementations of federated learning. As you can imagine, billions of devices, and to be able to learn patterns across all of them in a way that does not leak individual information was a daunting task. And Google actually built a lot of foundational techniques for federated learning towards this problem statement. So, in a nutshell, if you think about your device being the source of data for the federated learning, um, Gboard was built to train a portion of the model locally on your app, right, using your typing data, and only send the model updates, right, from the uh, processing of your local data back to Google, back to its headquarters, without actually sending the raw text, without sending information that would potentially leak in, you know, uh, privacy, uh, uh, you know, uh, privacy information about you, without leaking that. How do you send the model updates is something that they worked extensively on. And the model updates also have to make sense mathematically, right? You've got model updates from, billions of Android devices. How do you aggregate them? It's not a simple, a linear algebra equation, right? You've got to now think about how do you take those meaningful slivers of information and bring it back in, and then aggregate in a way that's secure. And towards this, they built the secure aggregation algorithm. What the secure aggregation algorithm in essence says is, if I have the sum of weights, I cannot engineer or reverse engineer the individual weights themselves, right? Given a sufficient time duration or a sufficient amount of sampling that I can do to get the sum of weights. So it's a non-trivial problem. They solved it using the secure aggregation technique, and that's what they released to the academia. And Gboard uses it, internally as well. So that's a great example of federated learning. I'm sure there are more examples. One of the earliest examples was something that I remember contributing to, which was, the search for extraterrestrial organization or intelligence. I think it was called SETI as a project. One of the earliest instances of distributed learning or federated learning. So they developed these apps, and these apps would run on your local desktop. And back then, desktops are, of course, the most common. And then they would run whenever you ask it to run, whenever you allow it to run, and then it would feed back information, receive information, etc., etc. So I remember that pretty fondly. In whatever shape and form I had contributed to looking for extraterrestrial intelligence. But yes, there are more examples nowadays in the world of mass consumption of AI-driven products. Okay, speaking of which, again, if you look at the action, where does the action happen? The action all happens on end devices, also called the edge, right? Naturally, the edge has featured increasingly more powerful devices. So you've seen the phone wars, right? Every phone manufacturer, Apple, Samsung, Xiaomi, etc. They've all tried to outdo one another with every new release of the phone with better hardware, better camera, etc., etc. But at the end of the day, it still is not going to pack the same amount of punch that a bunch of GPU servers on the cloud will have, right? So how do you take this really cool, sophisticated intelligence that GPT style um, architectured models can produce or can seemingly mimic, and shrink it down in a way that can run on a edge device which has nearly not as much GPU horsepower? That's basically the model compression for the edge topic. Um, Obviously, operations matter heavily here, right? It's not the choice of the algorithm alone. So we saw one example of it where if you take a conventional CNN, convolutional neural network, let's say a ResNet 50, it does great at image recognition, pattern mining. But if you take ResNet 50's gigabytes of weights and put it into a mobile phone, even one of the best high-end phones nowadays has only maybe 2 or 3 times more memory available than the weights of a ResNet 50. So that might not be the right choice of the model architecture to deploy on the edge, right? Instead, there are, for instance, versions of ResNet 50 which have been significantly compressed. Like for instance, MobileNet is one example, which is trading accuracy on one side, but it's giving you a size and a form factor which is more conducive for putting into a phone. So it's a choice we have, or the phone manufacturer has, to trade this off, right? So that kind of a choice of algorithm or network architecture is one way to deal with this problem statement. How do you compress the data, compress the model, that is? Then you've got to also have the model be lightweight enough such that it can run fast. It's not just a size, but also the architecture has to support fast inference, right? So this should also help you lower the cost and make it deployable on the edge. Then how do you give new updates to the model? We spoke about federated learning as the way to learn, but how do you propagate that back in a way that every local instance has the latest variation, latest update available to it? That's a significant operational challenge. And the third and the last part, which is also a unique challenge to edge computation, is oftentimes the edge is on edge is offline, right? Of course, it connects to the internet every now and then. Some cases it's always on, but in many cases it's actually offline as well. So how do you deal with local intelligence, local models executing when you don't have access to the internet? And how do you deal with the failover? How do you deal with the buffering that needs to happen, etc., etc.? Those are all operational matters. Now, if you really think about the motivation, many motivations exist, and one of the biggest is um, autonomous driving. So Tesla uses edge inference in cars for real-time decisions. It doesn't actually depend upon taking all the data, putting into like a Tesla cloud, and then bringing back the answer. That's just too much latency for very quick decisions that a car needs to make. So that's the motivation for you. Edge AI is actually extremely fast. It needs to be fast, and also it needs to be private. But the fact that it's constrained in terms of the hardware, the resources it has access to, makes it challenging. So that's why this topic is still an emerging topic, a lot of work to be done. Okay, the third topic is around how do you deal with a presence of an estate which spreads across multiple cloud and data center deployments. I can tell you that unless you're a really small startup or an individual, in most common settings, you will find multiple cloud vendors and or local data centers that the company has been running for a long time, and the data centers have been spread across multiple regions, and therefore they don't look the same. Even though IT has strived to make homogeneous tech choices, in most cases you'll find that they don't look the same. So your code or your software or your ML driven application has to be able to span across multiple cloud, multiple um, data center and cloud combinations, or multiple even data center combinations without even cloud involved. So this is what we call as multi-cloud / hybrid deployments. To be able to do that, you've got to obviously rely upon more open source technologies and open standards as opposed to proprietary technologies and closed interfaces, because vendor lock-in automatically locks you into a specific deployment model, and that precludes you from benefiting from multiple clouds or multiple hybrid deployments. So that's one choice you'll have to make pretty early on. But operationally speaking, you've got to also choose and design and work with software which abstracts away the infrastructure, right? So the fact that it's an NVIDIA GPU hosted on NVIDIA cloud versus a GPU that's on AWS versus a GPU that's on your local server should not affect the fact that your model needs to train on GPUs. Can your code deal with it today? Yes, PyTorch has given that kind of abstraction as an example so that you don't have to worry about these nuances. Can your code now build in the same level of abstraction such that it can run seamlessly on a GCP Vertex platform, but it can also run completely hosted locally on your local servers with Prometheus for monitoring, with Spark for data engineering, etc., without being dependent on serverless software or SaaS software from cloud vendors or PaaS software from cloud vendors. So that kind of infrastructure abstraction is a critical aspect of the operations related to multi-cloud. Security becomes a nightmare because you no longer have one attack boundary, which is usually the case with one deployment. You've now got an attack boundary that's so amorphous, right? That's so nebulous because it takes the shape of all the different deployment options that you have now available at your disposal. And you've got to now manage security across all of that. That's a challenge. The associated challenge is also governance. What does provenance mean? What does lineage tracking mean when you've got data flowing from one edge device into your central cloud where the data estate is, and then into another cloud where your model deployment or model training happens, and then that deployment gets used in an application or a website which is completely separate and hosted on, let's say, Cloudflare or something else. It's a pretty challenging topic, right? How do you deal with governance across all of this? What has to be done, right? Logging and monitoring becomes even more of a challenge. Observability becomes paramount, right? Absolutely necessary. If you thought observability is required in a single cloud deployment because there are so many services, think about multi-cloud. What does that mean, right? You've got a multiplicative factor on the number of services that you use critically, um, with every deployment that's available as an option. So observability becomes absolutely essential. Let's take a real world case study of Johnson and Johnson in the next slide. So the key takeaway is the more multi-cloud, the more portable or um, vendor neutral your code should be, right? That's the mantra that you might want to follow, especially for ML systems. So let's take a look at Johnson and Johnson. It's a multinational company. It's a Fortune 500, I believe. It's got so many different lines of businesses that each line of business can be thought about as its own independent ML family of use cases. Nevertheless, what they did do was to build global ML pipelines for 4 or 5 critical problem statements which are repeating across multiple lines of businesses. The first is supply chain optimization. Second is around marketing analytics. Third is around clinical trials, which is specifically for their pharma unit. And then quality control in manufacturing, which applies to both the pharma unit as well as the FMCG units as well. So multiple stages to how the pipelines are engineered. Um, we've seen these definitely in our model development lifecycle, but how do they deal with it, right? Especially with multi-cloud. For data collection, as a step, the data comes from multiple different sources. Like I said, it's coming from edge, coming from remote locations like hospitals and sensors. So they used a combination of both local data collection facilities, which is what is called as on-premise or on-prem um, uh, data collectors, and edge data collectors, brought them all together into edge data centers, and then fed it into a common data estate. Where is the data estate, which is basically the data storage? These were a mix of structured data, which was stored in Postgres, an open source RDBMS, and unstructured data, like in the form of medical scans and text. And they were stored on S3, which is an object store on AWS, very similar to GCS. And then some part of it was also object store, which is on-prem. The good part about object store technology is that it's one of the earliest cloud technologies to evolve, and therefore there is sufficient level of abstraction and standardization that's come in such that you can seamlessly move from one object store to another without having to feel that you're locked into a vendor. ETL pipelines work with the data that's stored and process them for engineering features and analytics and reports and things like that. So they chose Spark for it, being open source, and Spark itself ran on Databricks on Azure. So already you're finding some very interesting patterns here. Databricks, the choice of Databricks was something that they made because they wanted a platform as a service option for Spark, which was a lot more like SaaS, a lot more like software as a service, so that they didn't have to hand engineer the deployment infrastructure and things like that. But the choice of Databricks to run on Azure is quite interesting because the data estate itself is sitting on AWS and on-prem, right? And the data processing engine is sitting on Azure. So one of the biggest cost items you'll see when data becomes very large in size is egress, which means the exit of the data from a particular cloud. So in this case, I can imagine that the data exiting from AWS S3 and moving into Databricks on Azure would have cost them quite a bit of money. So the next step is the model training. Here they used a combination of XGBoost as the common algorithm, which is easy to explain, but also very powerful in its applicability for both classification and regression problems. They used PyTorch for deep learning, and then AutoML whenever they could for automated hyperparameter tuning and so on. Sorry. Where was this running on a combination of on-prem GPU clusters and GCP Vertex AI. Again, another big cloud vendor, and sitting seamlessly, it looks like, across from the other two clouds as well. Excuse me. The model registry, where all these developed models, both challenger and champion models, were registered, was on MLflow. We saw how MLflow gets used for it, and this MLflow was built as an instance on both Azure and GCP as well. So this allows them centralized tracking and lineage for ML models. CI/CD and monitoring, obviously distributed setup. It has to be distributed and catering to every single place where the model can be deployed or the data engineering pipeline runs. So GitHub Actions was used, GitHub Enterprise was used, along with some custom scripting, and some of the runners were running obviously on cloud, but some of them were also running locally because many of their estates were locally present on-prem. Last but not the least, the deployment of the ML models. They used a combination of web services exposing endpoints and as well as batch scoring, offline scoring. So for this, they used Kubernetes, and the hosting for that happened on Azure, and some of it was on on-prem servers as well. So a fairly complicated infrastructure landscape spread across three major public cloud providers, as well as on-prem instances based on where the data is originating and where the models need to be consumed. But this gives you a sense that if you were to get into the operations team of Johnson & Johnson's ML ecosystem, you will have quite a bit of challenge to maintain this and ensure that all the good things related to governance and stuff like that happens seamlessly. Okay, the last of the additional topics pertains to how ML itself is evolving to deal with emerging security challenges. One of the biggest challenges has been how much information does a modern ML algorithm reveal about the data that's actually being fed to it. This pertains not just to classical ML algos, but also deep learning, but more importantly and crucially, LLMs as well. So, protecting against the leakage, the misuse, and the inference possibilities is one of the biggest challenges from a security perspective. But sadly, also, it's not a solved problem. So, there's a lot of work to be done here, and something I hope some of you will take up. Obviously, the operational challenges are many. Some of it are, pertaining to how do you deal with data coming from different sources and merge them together without revealing information. We saw a bit of it in federated learning. Here, there is a technique called as differential privacy, so that these techniques rather work on the principle that no single data point affects the output detectably, which is a very interesting way to say, if I can perturb the input slightly, and I can do it one input at a time, and if I can observe the output variation, then I've built a causal relationship between that change in the input to that change in the output. And using a series of these causal relationship instances, I can potentially reverse engineer which set of inputs produce what kind of output. This is what happened in the model inversion attack that we saw in the week around security. Differential privacy as a technique tries to prevent this, right, by delinking the effect of one input on the output. So it's a great class of techniques. Um, the second way in which operationally you can deal with this is, don't work with raw data directly, but look at encrypting them and then doing all the different computations, including model training, weight tuning, estimation of loss, etc., etc. All of it happens on encrypted data. It's not as straightforward as taking an existing XGBoost and running it on encrypted data. You're going to get completely garbage results. It requires a development of, algorithms afresh. Of course, federated training is something that we saw as also one possible approach here. The real world example here is um, Google Chrome. The matrices that Chrome collects, those matrices are collected using differential privacy, such that no single user's browser history can be reverse engineered by looking at the overall metrics which have been collected in an aggregate, right? So it's a very serious violation if that happens. Google has been fined multiple times in the past with GDPR violations, I believe. So this is something that's a serious affair, and differential privacy comes to the aid of these kinds of distributed metrics collections. Roche, the pharma company, they train disease prediction models using hospitals' owned data. So the data belongs to the hospitals where the patients are registered, but the pharma company, being global, needs access to that data so that they can improve clinical outcomes by giving better quality medicines. One of the ways in which they do it is using something called as multi-party homomorphic encryption of the data, right? So that there isn't any single party which has access to the data by itself. Um, so you can read up more about it in homomorphic encryption techniques. So the key takeaway here is, identity security is becoming even more important in this age of edge consumption of AI, right, on our devices, on our laptops, etc. And crucially, the governance regulations around it in different countries have not caught up to the extent that some of the mature markets have already defined. So how do you proactively defend yourself as a company, as a maker of ML models, from regulations that can happen at a later point in time and can affect you retrospectively, right? So that's something to keep in mind. That's one of the reasons why privacy preserving ML should be at the heart of almost every single ML use case which touches end consumers directly. Okay, the last of the topics is ground truth for LLMs. It's a massive area of research, but it's also a massive area of investment. So as of the time of this recording, two of the largest players in this space have been acquired or have been quasi acquired by some of the big AI players like Meta and Google. So one such company is Scale.ai as an example. So these companies have been producing curated data sets which are necessary for LLMs to provide meaningful results without hallucination. So the ground truth that they correct or they create is absolutely essential for the modern wave of AI that's catching on. So how do you create this ground truth data sets? It's not a simple question of, doing what Amazon Mechanical Turk did, right? Which is just farm out ground truth creation to a bunch of humans and then collect the results back Like there are sophisticated algorithms, there are synthetic data generation techniques, etc., etc. Auto labeling, human in the loop systems, active learning pipelines, all of those are operational concerns here. Then you've got to also worry about what if two different voting agents on a ground truth label do not agree, right, on that particular label. How do you deal with building consensus? How do you deal with breaking ties, or how do you deal with conflicting labeling requirements? Those are all quite interesting problem statements in and of themselves, right? So Scale.ai, like I said, they powered annotation pipelines for very large ML foundation building companies like OpenAI. But Meta got interested, and Meta, uh, you know, bought over a majority stake in the company, got the founder into Meta as a like like a like a AI head or whatever. But then the company itself continues to remain, you know, as an independent organization. What would happen to it later on, we don't know. But at least this class of problem statement is something that's of immense interest. Um, so it should apply to. I mean, the interest should be applicable for the Indian market as well, because naturally the LLMs that we want in vernacular need ground truth in vernacular as well, and there isn't too much of that right now. Okay, so I'll take a pause here. In the next video, I'll summarize some of the closing thoughts related to um, the arc of evolution that AI systems are going through and what it means for you as operational engineers in the ML world.